What's going on? What in the world? If y'all can hear me, I'm so sorry. This thing is being really slow. If y'all can hear me, my computer is basically acting like it's frozen. I have no idea how long this is going to take. I can't even see the Zoom screen.
We can hear you, just so you know.
Okay, cool. Yeah, my computer did some big fancy update, and it is taking forever to go through the issues. I'm really hoping I don't have to cancel class tonight. And I'm sick on top of it, so everything's going so well.
Is the class already recorded and on YouTube or no?
No, I have to piece everything together, so I would still have to do that. So it probably wouldn't go up until tomorrow, depending on how things go. But still hoping that I can get it to work right now within the next 5 or 10 minutes, hopefully.
Okay, gotcha.
So thank you for your patience, everyone. All righty. So that only took 20 minutes. Well, I mean, 30 if you really go with from when I tried to start everything. So again, thank you so much for your patience with this. This was kind of unbelievable. Technology, though, what are you going to do? You got to roll with the punches. So as a reminder, Your test 2 is currently available today, tomorrow, and Wednesday. It is due 11:59 p.m. on Wednesday. Section 3.8 homework is due today. 4.1 is going to be due on the 25th. It's just going to let me type. We will finish 4.2 today. We were supposed to finish 4.3, but we will not finish it now, thanks to losing 20 minutes, unfortunately. So 4.2, we'll say, is due in a week on the 28th. We'll get through as much of 4.3 as we can. I really don't know exactly where I'm going to stop because I usually figure that out in advance, but having lost 20 minutes, I don't 100% know. I'll figure it out. Maybe I'll have time to do that during the break. So I don't really want to waste any more time. Let's go ahead and get into the lecture, picking up where we left off, 4.2.
In 4.1, we had our integration formulas, and we didn't get a ton of them. The first one we got was our power rule. Add one of the exponent, divide by the same value, but your original exponent's not allowed to be a -1, and by -1 I mean when the x is in the top. So this was the one case we have to pay attention to and not use that formula for. This wasn't an issue with derivatives, but it is with integration. We also had the constant rule. The integration of a constant was the constant times x, and that's because the derivative of a constant times x is the constant. We also said that coefficients of polynomial terms, or just basic functions, can just be pulled out of the integration. That's what this represents. It says that all you do is multiply that number by the integral of everything else. We also said additions and subtractions don't really affect integration, but multiplications and divisions do. We also pointed out that there is no product or quotient rule. We're going to have some fancier stuff to have to use. We'll wait on that. And then we also gave you the exponential and logarithmic integration rules. And when I say logarithmic, I mean the integral of 1 over x is the natural log of the absolute value of x, unless you claim that x is positive, in which case you don't need the absolute values. The integration of an e to the x, so both of these are natural exponentials, no base 10 or anything like that. The integral of e to the x is e to the x because the derivative of e to the x is e to the x. Just this extra c thrown in. And then we did give you a special case. This is kind of a special case of a formula we'll see later, but it's such a simple case, we go ahead and give you just the flat out formula. This is kind of like the chain rule for integration, but going backwards. But I don't want to say it is the chain rule because, again, it's a super simple case. So arguably we give you like 5 formulas in this section that we will continue to use over and over and over and over and over. They won't go away for the rest of the semester. You need to know them now, you need to know them tomorrow, you need to know them July 25th, you need to know them July 30th, etc. And we did, like I said, a whole bunch of examples. And I want to point out something before we do this last topic. Oops. I want that to be in black. The integral of e dx. This is a problem I intended to do last time and skipped. I was going to save it for the next section, but I'll just go ahead and do it now. The integral of the integral of e dx. This right here is not the same thing as this, e to the x. It's not the same thing as this, e to the 4x, e to the 2x. This, believe it or not, does not use this formula. The reason being, this formula is for things that are e to an x, or e to a 5x, or e to a 7x. That e has to have a variable in the exponent. This e does not have a variable exponent. So there is no variable exponent, which means this is like the integral of a dx. It's just a constant. We said that the integral of a constant is just that constant times a variable plus another new constant. So the integral of e dx is ex plus c. Because e is really just a number. It's 2.7 and some change. So this is just the integral of 2.7. That's like integrating 3 or 5 or 9. It would be 3x or 5x or 9x or whatever number you've got. So make sure you see the difference in this versus this. This is just a constant in the first one we did. This is an exponential, which has the exponential formula because of that. Okay. So last official topic of the section. Please don't do that. And it's going to do that. Arg. What in the world? Every time. Trying to decide how I want to do this. I'll just put it at the end. It's fine. It's fine. Finding the constant of integration. How do we find the c? You're given an initial condition. On the function after it has been integrated, find c. An initial condition looks like capital F of A equals B, or little f of A equals B, depending on the original problem. If your problem is this, oops, my dx. If your original problem says that the function they gave you is a derivative and you're finding the actual function, and you have your constant added in, the initial condition would look like this. F of A is equal to B. But if it looks this way, if we give you the original thing written as a normal function, not its derivative, when we integrate a regular function, that's when we go to the capital letter. And in that case, the initial condition would be capital F of A equals B. Again, it just depends on the original notation. Did they give you a function written as a derivative, or did they give you just a function written as a function? Because if they give you the function written as a derivative, when you integrate, you don't use a capital letter. The integral of this is this because the derivative of this is this. But when they just give you a regular old function and they say to integrate, this wasn't a derivative, so we don't go to a, skipping out on writing that little dash. That's when we go to the capital letter. So the hierarchy is like capital letter, lowercase letter, F prime, F double prime, F triple prime, working your way down. So again, you have to pay attention to the notation, but you're never going to be plugging an initial condition into the original function that you were given. You're going to be plugging it into the integrated function. That's the main thing to account for. Either way, you're plugging in after integrating. Otherwise, you won't see the C. Sorry for the terrible pun, completely unintentional. So how would you solve for it? Now, the solving of this is not difficult. It's straight up algebra. It's plug in a number and then solve for a variable, the variable being your c. So let's try it out. Let's see, what example are we up to? Example 6. And let's say a little lower first of all. Integrate the given function and find the constant of integration. A. We're going to write this as f prime of x is equal to x squared plus 1. And then our initial condition is going to be f of 0 is equal to 8. See, this doesn't say f prime of 0 equals 8. This says f of 0, and the given function was an f prime. Someone just asked if anyone else hears a clicking noise every time I begin to speak. Please feel free to answer that in the chat if you do. I'm not sure what's happening. I know the house behind me is doing some pretty major construction. I hear like some banging, but I have a feeling that's not the clicking you're referring to. Is this, do you hear that clicking? Is that what it might be? That's my pen. Maybe I'm just being a little aggressive with my pen today. No, you know that noise. All right, well, I'm sorry. I hope it's clear enough for me to hear. I'm sorry if it's annoying, all these fun things. If it continues to be a problem, I'll pull out my headset again, but I'd rather not if I don't have to. Okay, so this is the function we're going to integrate. So we set this up as the integral. I'm going to switch my color though. The integral, and I got to put it in parentheses to make sure that the dx part is set up correctly. So the integral of x squared plus 1, then dx. So this is just the power rule. You're going to add 1 to the exponent and divide by the same value. So adding 1 to 2 is 3. So you get x cubed over 3. Again, you add 1 to the exponent, then you divide by the same value. Plus, this is a constant. When we integrate a constant, you just throw the variable next to it. So I'll write the 1 to be clear. So this is the 1 that we originally had, and you just give it an x. And if you don't believe that, take the derivative of 1x, you should get 1. That is something I highly encourage you to do while you're starting to learn this integration process. Do this and then go backwards to check it. But don't forget our plus c. There's nothing else we can simplify with this. So that says that f of x, because we integrated f prime, this is our f of x, is equal to x to the third over 3, plus, I'm not going to write the 1 now, plus the c. So again, that's a lowercase f. It's not the prettiest f. I want to make sure you can tell that's a lowercase. There we go. So now all we do is we're going to use this initial condition and plug the 0 and the 8 in appropriate spaces. This is where the x goes, the 0. So the 0 is going to be the x's. Then the 8 is what the function turns into. So you're going to turn this into the 8 because we're actually showing that the function value is 8. And then 0 is going to go here and here, because that's what the x is. So the f of x becomes the 8, the x's become the 0s. So again, f of x is going to be 8 when x is 0. So plugging all that in will give us the following. Instead of writing f of x, I write 8 then the equal sign. Instead of x cubed over 3, it's 0 cubed over 3. Then plus instead of x, it's 0. But the c stays. We don't plug anything for the c in. We're finding the c. That is what's going on here. Well, 0 cubed over 3 is 0. 0 divided by anything is 0. 0 plus 0 is 0. The whole right side is 0 except for the c. The left side is 8. So you get 8 equals c. It's almost no work to do, in fact. It's extremely simple. So all we do is go back in, plug this number in where we had a c written before. That's going to go there. So our function, f of x, which was the integral of f prime, and accounting for the initial condition, is x cubed over 3, or 1/3 x cubed, plus x plus 8. Now that c could have a negative sign. That's always possible. Then if this was a -8, then this would be a -8, is all I'm saying here. So there is no more plus c. The c could also be 0. These are all possible scenarios. So this is how we find a constant of integration. Let's try another, and let's do it with the other notation. Instead of giving you f prime, I'm going to give you f of x. So f of x is equal to, let's go with 6x squared minus 4x plus 2. And I'm going to tell you that f of 1 is equal to 9. Capital F. I'm sorry, I'm messing up. Capital F of 1 is equal to 9. See, because we're supposed to be integrating the original function, integrating a regular lowercase f gives us an uppercase f. That's the hierarchy. So capital F of x, and I'll even write this extra step at the beginning, is the integral of f of x dx. So that's the integral of, can I do this? 6x squared minus 4x plus 2 dx. Is this okay? No, it's not okay. It's not okay because we don't have the parentheses is all. And then we just straight up apply our power rule. All of these are polynomial terms, so just power rule it. The 6 and the 4 won't have any effect, just leave them as multipliers. The x squared, you'll add 1 to its exponent. 1 plus 2 is 3. And then you divide by the exact same number that you just got. Again, that's the power rule from earlier. Minus 4, leave the minus 4 there. Now there's no exponent written here. If we don't see an exponent on a variable, we assume it's a 1. So there's an implicit or implied 1 there. 1 plus 1 is 2. So this becomes an x squared, and then over 2, because these numbers must match. Then plus the integration of 2, since that's a constant, it's just 2x. And then we, of course, have our plus c at the end, which is kind of hidden there, but there it is. So our integrated function, the 6 divided by the 3 is a 2, so that's 2x cubed, minus the 4 divided by 2 is a 2, and that's an x squared, then plus the 2x, lots of 2's, plus the c. Now last class we would have stopped at this point. We wouldn't have been given the initial condition, but now we have it. We know that if you plug in 1, the whole thing turns into 9. So if you plug in 1 here, here, and here, this whole thing should be equal to 9. So in other words, f of x is equal to 9 when x is equal to 1. So this function becomes 9, and the x's become 1s. So 2 times 1 cubed minus 2 times 1 squared plus 2 times 1 plus c. And from here, it's just straight up algebra. 1 cubed and 1 squared is 1. 2 times 1 for all of those is 2. So that's 9 equals 2. minus 2 plus 2 plus c. The 2 minus the 2 in the front cancel. So you just have 9 equals 2 plus c. Subtract 2 on both sides. And you'll get, sorry about that, 7 is equal to c. So our integration constant is 7. So the answer is 2x cubed minus 2x squared plus 2x plus 7. The initial condition gives us one answer instead of literally trillions of answers. The answers before, when we had a plus c in there, that c was undetermined. Because remember, when you take the derivative of a constant, you get 0. So that constant is there because we don't know if there was originally or not. But when we're given an initial condition like this, capital F of 1 equals 9, when a lower case function is prescribed, or a lowercase f when the derivative is prescribed, now that is what enables us to figure out what the original constant would have been. So when you go and take this derivative, you will still get the original function because the derivative of 8 goes away. The derivative of the 7 goes away. Not all problems are given an initial condition. Some of them are, some of them are not. So if you aren't given an initial condition, you will have a C in the answer. When you are, you won't. Most word problems usually have an initial condition. And I've got a couple word problems I'm kind of setting to the side for now that I want to come back and do once we get through some more material. But I want to get the basics done first before I get into word problems and kind of complicating things, if you will. So with that being said, we can call 4.1, excuse me. I'm still thinking the old textbook in my head. 4.1 completed. All right. So let's make a new document. Let's hit enter for about 17 pages worth. I'm about sick of that issue, right? Okay. 4.2. This title is Antiderivatives as Area. I mentioned last time that the way that we cover this section is going to be interesting, to say the least. Most of the homework problems in here go through a much more complicated process of approximating area via what we call Riemann sums. And what exactly a Riemann sum is, we're going to get into. But the problem is they're very, very time consuming. So it's not a problem that I really like to discuss in super great detail and give you tons of homework and tons of test questions on. However, it is still an important concept that ties in what we were just doing to the geometry of calculus, because when we talked about derivatives, we figured out that they were slopes at points. Well, it turns out that integrals, or antiderivatives, whatever name you want to give it, they relate to, well, spoilers, area. So derivatives are used to talk about the slope of a function. Antiderivatives, or integrals, are used to talk about the area of a function. And you might go, well, why would you ever want to know the area of a function? What's the point of that, right? Well, let's have a leading example just to kind of set up this concept. We got somebody that's going to be driving 15 miles an hour on a little motor scooter. So we got Bob drives, and I think the textbook's name's Emma. I don't care. Bob, Emma, Jane, whatever. Bob drives at 15 miles per hour. He's on a little scooter. For an extended period of time. And when I say this, my brain just goes to a classic movie, Dumb and Dumber, to people on a scooter for a very, very, very long time. Sorry, I know I'm a little silly, but can't help it. So Bob drives at 15 miles an hour on his scooter for an extended period of time, an hour, a day, a month, something like that. Let's ask a couple of questions. How far has he traveled in 1 hour? How far has he traveled between the, I'll fix that in a second, the first and second hour? How far has he traveled cumulatively between the first 2 hours? And can you think of a function that gives the total driving distance? Picture's worth 1,000 words. All right, so Bob drives 15 miles an hour for an extended period of time. I don't think that a lot of people are at this level are going to have a hard time figuring out that if you're driving 15 miles per hour, you're going to go 15 miles in 1 hour. Oh, I didn't fix my typo. Also give you a few minutes to write all that. If you drive your scooter at 15 miles per hour, that means in 1 hour you go 15 miles. It's literally 15 miles per 1 hour. Then, how far has he traveled between the first and second hour? This is asking the same exact question, just phrased slightly differently. It's asking how far does he travel in an hour, but specifically from, minute number 60 to minute number 120. Well, that's still 1 hour's worth of time, which means he still travels 15 miles. How far has he traveled cumulatively between the first 2 hours? Well, 15 miles for the first part, 15 for the second part, so 30 miles. You just add them up. Can you think of a function that gives the total driving distance? So that's not really related to question B. It's more related to questions A and C. After 1 hour, he went 15 miles. After 2 hours, he went 30 miles. So for part D, we're trying to think of some function of time. So let's use t for time. So that time is going to be in hours. That whatever this function is involving t, if you were to plug in 1, you'd get 15, and if you were to plug in 2, you'd get 30. Now, if we had lots of time together, we could sit here and try and do slope analysis and all sorts of things. But I hope that you've had enough practice with linear functions with no intercepts to figure out that this is just 15 times t. If you plug in 1, 15 times 1 is 15. If you plug in 2, 15 times 2 is 30. And this works even further. 3 hours, 15 times 3 is 45. He would go 45 miles, 15 in the first hour, 15 in the second, 15 in the third, for a total of 45. So f of t is in miles. T is in hours, f of t is in miles. Now, I came up with this kind of off the top of my head, if you will. I could have, again, like I said, used point analysis, done 1,15 and 2,30, found the slope of that, assumed that this was a proportional function, which makes it linear, and all sorts of good stuff. The point of all this is, how do you go from just this fact of 15 miles an hour to get this answer of 30 miles? That's what calculus is building us towards. How can we just know that he drove 15 miles per hour and get 30 miles without making this function up off the top of our heads? How could we find this function using calculus? I am writing terribly there. I want to type it. Well, remember that velocity is the derivative of position. D prime of t is equal to v of t. This means if you go backwards, if you think antiderivatives, the integral velocity is position, which is how far you've gone. i.e., the integral of velocity is equal to distance or position. Now, when you integrate, of course, you've got this integration constant thing going on. So this suggests that if we integrate 15, which was the velocity, it's a constant speed, there's no variable with it. Our velocity was 15. So if we integrate this, we should be able to get a function that would tell us our position. So let's integrate this. The integral of 15 dt. Now that's a constant. The integral of a constant just gives you the constant times the variable, but this isn't an x because we're integrating over time, dt. So this is 15t plus c. Notice that this thing right here and this thing right here are the same. So that's a good sign, but what about this plus c issue? What's going on with that? So what's up with that plus c? Pause on that idea and finally get to the picture is worth 1,000 words bit. Finally. All we've done so far is we've used basic logic and reasoning to get that, oh, he went 30 miles in the first 2 hours. We also built a function based on simple algebra skills. We made an association between derivatives and integrals in relation to our distance, velocity, and acceleration formulas, their derivatives with respect to each other. So if the derivative of distance is velocity, the integral of velocity is distance. We integrated the function, we got a familiar looking piece, but then there's extra constant in here. So if you plugged in a 2, this 15 times 2 would be 30, which probably makes you think we'll just ignore the c. Like I said, pause on that idea. It's not that you ignore the c. It's something happens to it that we'll get into in the next section. But now let's again go to the picture's worth 1,000 words. Let's graph velocity function versus time. Now the velocity function is constant, so it's a horizontal line. Height we'll do this. So velocity versus time, velocity, time. So a velocity, it's constant at 15 miles per hour. So here's our 15. And no matter what the time is, whether it's 1 hour in, whether it's 2 hours in, whether it's 3 hours in, whether it's 1,000,000 hours in, this right here is our velocity function. It's just 15. It's not 15t. That was the position function. The velocity was just 15 miles an hour. It was constant. Now, what I want us to do is, let's imagine that we drew vertical lines on the 1 and the 2 separately. So let's draw vertical lines at x equals 1, which is 1 hour, then x equals 2, which is 2 hours. And again, we're going to do this as separate problems. So let's draw a vertical line here. And I'll do it dotted because it's not really anything. And what I'm going to ask you to do next is find the area of the rectangle surrounded by the axes. Find the area of the rectangle surrounded by the axes. What I mean is this area. It's a rectangle. If you don't know how to find the area of a rectangle, I'm terrified. It's length times width. So this thing has a width and a length, or height and width, however you want to say that are very predictable. You're starting at 0 here and 1 here, so that width is 1. I'm going to do this in blue. So again, 1 is this width right here. And then the height of the box, it's going from 0 to 15, so the height of that box is 15. So that little area, let me call this area 1, would be 1 times 15, which is 15. Now guess what? The fact that this is a 15 is not a coincidence. Remember when we found out how far I traveled in the first hour? It was 15 miles. And this is a 15. That's not a coincidence. Now let's do the other one. So now we'll do this region, which we'll call little a2, a little 2. And that is very similar to the last one. This width right here from here to here is 1. I should have done it in a different color. Let's pick a different color. Let's go with dark green. So this distance right here is still 1. This vertical distance is still 1. So area 2 is 15. 15, the height is 15 before anyone corrects me. Sorry about that. Is 1 times 15, which is 15. And guess what? That's going from hour 1 to 2. It's not a coincidence that how far he drove from hour 1 to 2 is 15 miles. What I'm hinting at is that these areas are how far Bob has gone from hour 0 to hour 1, or from hour 1 to hour 2. Now let's do the whole thing. Let's go from 0 to 2. So I'm going to redraw everything. So here's the function at a height of 15 to represent our speed of 15 miles an hour. Then we're going to go from 0 to 2. I didn't do the dotted line along the axis the first time. It's not really important. I mentioned it. We're going between 0 and 2, so we're finding this area. So this width would be 2. We're going from 0 to 2, so that's 2. The height is 15. So the area, let me just call it capital A, no subnotation, would be 2 times 15, which is 30. And guess what? It is not a coincidence that the answer of how far he traveled between the first 2 hours cumulatively was 30 miles. This shows that the area under the curve, and I'm saying curve in quotes because yes, these are lines, but we're generalizing the area under the curve of a function. It's just the integral of the function from 2 given x values. The area under the curve of a function is the integral of the function. Derivatives are slopes, integrals are areas. Now in the last section, we never actually did any areas because we didn't say to go between these two values. It's only area when we tell you to go between two values. See, on this one we went from 0 to 1, and then we went from 1 to 2, then we went from 0 to 2. Again, in the last section, we never plugged in two x values. You might say, well, you plugged in 1. Yeah, we did 1, but not 2. That 1 was just an initial condition that enabled us to find C. In fact, when you're doing these problems, C is completely irrelevant, as we'll spoil in the next section. Now, you might be thinking, well, Mr. Beckner, these are just lines. How does this actually tell me that this really works? That the integral function can be used to find the area under a curve. So while you're not necessarily trusting me yet, let's build up our functions. Let's do a little more of a complicated one, then a little more of a complicated one, and see what we can get out of this. So let's do another example. Call that example leading example. So we'll just go, I guess, example 1. Example 2. I lied. In quotes because, like I said, not necessarily assigning everything, but this is still important conceptually. So for f of x is equal to x. I don't need to write this, I can type it. For f of x is equal to x, the standard linear function with a slope of 1 and no y-intercept. Show that the area under the curve, again, curve in quotes basically, from 0 to 4 agrees integration. So let's do the integration first. If f of x is equal to x, capital F of x is the integral of lowercase f of x. So we're integrating x times dx, which is x squared over 2. This is an x to the 1, so you add 1 and divide by the same value. Again, these numbers have to match. And then you go plus c normally. Again, as I said, coming up, we'll talk about why the c is going to go away very short. So there's our integral. So if little f is x, then uppercase F is x squared over 2 plus c. Let's do the graph. Here's a graph. And, excuse me, I'm really only worried about the positive region. We're going from 0 to 4. This is the line y equals x, or f of x equals x. At 1, we have a height of 1. At 2, we have a height of 2. At 3, we have a height of 3. And then at 4, we have a height of 4. So 1, 1, 2, 2, 3, 3, 4, 4. Those are 4 points of that line. You only really need 2 of them, but you get the point. So we want to find the area under the curve from 0 to 4. That's why I stopped at 4. Now, this thing starts at the origin, and then it goes up to 4. So if you want to do that little divider, that's where we're stopping. So the area that we're finding is this right here. This is our area. Now, I didn't give you any physics relationship to this, just math. What does that shape look like? I just pulled it, didn't I? This sloped side along with this vertical and horizontal side that looks like a triangle. Triangle areas are predictable. It's 1/2 the base times the height. Well, this triangle has a base of 4 from here to here, and it has a height of, well, coincidentally, 4 as well. They don't have to match. So that area should be 1/2 of 4 times 4. Half of 4 is 2, 2 times 4 is 8. So the area under this, quote, curve or line, as it is this time, is 8. Now let's go back to the previous example. The areas, the 15s and the 30s, seem to be us going from 0 to 1 or 1 to 2 or 0 to 2 respectively. Let's ignore the 1 to 2 part. Let's just look at the 0 cases. So from 0 to 1, it was 15 miles, and that was the area under the curve. From 0 to 2, it was 30, and that was the area under the curve. The C didn't seem to have an effect when we went from 0 to something else, when we went from 0 to something else. So going from 0 to 4, because that area is 8, that suggests that if I plug in 4 to this function, the answer is probably 8. So let's say, does this match f of 4? Excuse me. So capital F of 4, remember we're using this function, not the original one. It's x squared over 2, so 4 squared over 2 plus c, which is 16 over 2 plus c, which is 8 plus c. The fact that this is an 8 and this is an 8 means that we're probably on the right track. So again, note C becomes irrelevant. Irrelevant. It's not gonna matter. So now you're thinking, all right, well, why would we ever do the calculus? Why don't we just do this geometrically? Because if these aren't a horizontal line or a sideways line, this is insane. trying to find the formulas for areas under a parabola or a cubic or a quintic or a rational or a radical function, you're not going to know these. These were super basic shapes. We have a rectangle and a triangle. Most of the time, we're usually finding the area under an actual curve, like f of x equals x to the third minus 5x squared plus 2x minus 1. And if you go to graph that, x to the third minus 5x squared plus 2x minus 1. So maybe you want to find the area under this curve from 0 to 4. So you'd be finding the area under or above. It could be above too if it's below the x-axis. So you're trying to find this shaded region, like 0 to 1, 2, 3, 4. Kind of stopping here. Here. Sorry, I'm pointing at the wrong thing. What formula gives you the area here? I have no idea. You'd have to integrate it. That's why we don't want to just graph it and then try and use basic geometry, because 99.99% of the time, you can't do that. So for now, what could we do using geometry? In basic geometry, we can approximate the area under the curve by dividing it into many small rectangles. There are many other methods than this. But this is what we will use. Again, they call it a Riemann sum. R-I-E-M-A-N-N. I couldn't remember if there was 2 N's or not at the end. I had to look it up, and it is 2 N's. So again, this is known as a Riemann sum. R-I-E-M-A-N-N-S-U-M. Let me show you what we're talking about here. So you got some function. And you're going to go from A to B. So 0 to 5 or 1 to 12, whatever. And this is your curve. So this is our original f of x. And we want to find the area from A to B. So I'm gonna show the area we're trying to find, but then I'm gonna erase these diagonal lines. And I drew that too far. This is showing the area we're trying to find. But we're going to approximate it. We can't do a Riemann sum and find this exact answer using these little rectangles. So what we do is we divide this up into a number of regions. So we'll have a rectangle, let's say at this height here, and I'm going to try and make this as even as I can. I'm going to make them pretty wide. So here's your first rectangle, and then your second rectangle, and I'm going to change the colors each time. So the second rectangle would look like this. Then the third rectangle, I'm just going to keep going between red and blue, would look like this. Then the fourth one would look like this. The next one would look like this. And I'm getting a little wider at the end, but that's okay. It's not the point. And then this. So using basic geometry, we can approximate the area under the curve by dividing it into many small rectangles. So we find the area of all these rectangles because those are easy to find. It's just length times width. So you take this width times this height, this width times this height, this width times this height. Now notice that these rectangles, because the function is at different heights on the left and the right side, you can't have them touching. So like this first blue one is below the curve here. This one is about the same because of it going up and then back down. But then the rest of these are actually a little over. So this first one is an under approximator, but then the third, fourth, fifth, and sixth are over approximators. Now this was attaching them to the left side. So I've anchored these to the left side. So again, I'm having points here, 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 and here. Those are the heights that we would actually use for the calculations. So this is a left side approach. Or, let's do this one more time. I'll try and draw this the same as best as I can. That's already a bad start. Good enough. So this is a left side approach. This will be the right approach, right side approach. So we're going from A to B. B was on the bottom. There we go, blue. So now I'll use the right side. So when I make my first rectangle, instead of starting from here, I'm not going to do this. This is no longer going to be the rectangle. I'm going to anchor it to the height of the right side. So in other words, this point needs to be a little higher. Then for the next one, again, we're going to use the right height. So it appears to be about here. I got 1, 2, 3, 4, 5, 6 of these. Then we'll go with a blue one. Let me extend that. So now the right height, which is about here. I know that one looks a little wider. Again, just forgive my poor artistic ability with this. And then again, right height, so about here. And the right height, which is about here. And then the last one, the right height is definitely here. There we go. So again, the left approach, you use the heights as the left side of the rectangles. The right approach, you use the right side of the rectangles for your points. Does it matter which one you use? Well, it depends on whether you want an approximation that's too big or too small. With this left approach for this example, there's a lot more over approximations, like this one's a little too much, a little too much, a little too much, a little too much, whereas this one's just a little too less, not quite enough, if you will. So this one probably over approximates the area, whereas this one, most of the rectangles are below, there's only one that's above, and that's this one. So this would probably under approximate it. Now it depends on your function. All left approaches don't over approximate, some of them under. Same for right, that not all of them under, some of them over approximate it. And what's cool is another extending tactic, like I said, there are many of these tactics. What you can do is do a left approach, do a right approach, average them, and I bet the average is probably closer than the left and the right approaches for normal acting functions. Notice I'm throwing quantifiers out there, it's not a guarantee. Instead of using rectangles to approximate these areas, you can use trapezoids. So you can actually add on a little triangle to the top of each of these and add or subtract them. So like this one, you could add a triangle to it and add it. This one, you could subtract this little triangle. That would give you an even closer approximation, but it's even more work. And we call that the trapezoid method. So one thing that's consistent with these is the widths must be the same. Where's my mouse? The widths must be the same for each rectangle. Choose or given. You then find the x values, plug in to find heights based on the width of each rectangle. Call the width of each rectangle delta x. That little triangle represents a change. We've used that symbol to denote slope before. Triangle y over triangle x was the change in y over the change in x. And this represents the change in x values. Typically, smaller this delta x is, which is the triangle means delta, the better the approximation. So if you use a width of your rectangle as 5 versus using a width of 1, a smaller width means you're going to have more rectangles, which means it'll be a more accurate approximation. If you use a width of 0.1 or 0.01 or 0.001, it's going to keep getting better and better and better. And some of you might already know or have an idea what I'm leading to. Back when we were doing derivatives, we took the distance between 2 points and we slowly and slowly merged them together until they became the same point. That's the exact idea we're doing here. We're going to take that delta x and we're going to make it infinitesimally small. We're going to take it to 0. And when we do that, it turns into that dx thing, and it ends up giving us an integral. That's the ultimate aspect of all this. But let's do one example with this Riemann sum, just to give us an idea of how this would flow. We'll do it with a simple function, and then I think we can call it for this section. So example. Approximate the area under the curve x equals 0 to x equals, let's go with 5. With delta x being 1, function f of x equals x squared using a left-sided approach. If you want to have fun with this, do a right-sided approach and compare your answer. So we're going from 0 to 5 with a width of these rectangles being 1. So let's draw up the picture so we have a good idea of what we're going to be looking at. We're going from 1 to 5. The height of 5 for x squared is going to be 25, so I know I need a 25 way up here at 1, 2, 3, 4, 5. Now, I should really have these a little more squished together on the horizontal axis, but I want you to be able to see the details of the triangles. So then we know that f of 4 squared is 16, 1 squared is 1, 2 squared is 4, 3 squared is 9. So, trying to think how I want to do this. This is probably about 16. Then we'll have this at about 9, then about 4, and a height of 1. So there's our x squared graph. Basic parabola. Everyone should know what that looks like. Forgive me if the heights aren't lined up perfectly. Not the point of the problem. So we want each of these widths to be 1. So going from 0 to 1 would be one rectangle. Going from 1 to 2 would be one rectangle. Going from 2 to 3 would be one rectangle. From 3 to 4, from 4 to 5 would be our one rectangle. Again, f of 0 is 0, f of 1 is 1, f of 2 is 4, f of 3 is 9, f of 4 is 16, f of 5 is 25. Now we said to do a left-sided approach, which means we're anchoring to the left sides to draw our rectangles. And I'm actually going to work from the right side backwards because the first one might throw you off. So when I want to find the last one, when I want to find, well, first of all, we're going overall from here to here. So this is the area we are finding. Forgive me for being a little over exuberant there. But we're approximating. So for the right triangle, the furthest right one, it has to be this. This has to be the triangle because we're using a left anchored approach. If I was using a right-sided approach, I would have done it this way instead. So that's the first rectangle from the right. Again, I'm working backwards. The next one, it would be this. Again, each of these delta x's is 1. Each of the widths of these is 1. Then this would be the next one. Anchoring it to the left side of the curve. Then this would be the next one, anchoring it to the left side of the curve. And the last one, that's a height of 0. There's actually no rectangle because if you have a height of 0, I mean, that's a non-existent rectangle, right? If I had done a right-sided approach, there would be a rectangle on that one, and it would have a height of 1. So this is definitely going to be an underestimator because we don't have a rectangle here, so this area is completely missing. This one's going to be missing this little chunk. This one's missing this chunk, and this chunk. So this will be an underestimator. Now let's find all of these. So again, each of these little widths, this shows that the delta x is equal to 1. This shows that the delta x is equal to 1 because the widths are 1, because the widths are 1. I'm not going to write it for all of them. So the total area should be approximately 1, 2, 3, 4, 5, the sum of all these little areas, A1 plus A2 plus A3 plus A4 plus A5. The area of the first one, there's no rectangle, so it's 0, plus the area of the second one, this would be A2, that has a width of 1. All of them have widths of 1, so 1 times. And then the height. The height of this rectangle is 1. Again, it's all widths times heights. All of the widths are 1. Plus, then the next one, this is area 3, still has a width of 1, but its height is 4. See, 4. Plus, the fourth one still has a width of 1 times, and its height is 9. 9. Plus, and then this last one over here, the width is 1 times its height, which was 16. We actually don't even use the 25. If we did a right-sided approach, we would, but it was still nice to know that. So this is 0 plus 1 plus 4 plus 9 plus 16, which is 5. 5 plus 9 is 14. 14 plus 16 is 30. Again, this is the approximate area. Is it 30? No. Is it close to 30? Yes. In fact, I'll tell you the exact answer. It would be 41 2/3. So 41 2/3 is kind of close to 30. You know, it's 10 off. That might not make you too happy. And that's because these rectangles are pretty large. If you wanted a better approximation, then you'd use delta x equals maybe a half or 0.1 or 0.001. But the smaller you make your delta x, the more rectangles you're going to have. If I make the delta x a half, that means I'm going to need 10 rectangles. If I make the delta x is 0.1, so if your width is a half, that means it's going to take 2 rectangles to go to the first one, so 10 rectangles needed. If you let your delta x be 0.1, so that means it takes 10 of them to go a whole unit, which would be 50 needed. If you use 0.01, that would be 500 rectangles. You can see why this is annoying to do by hand. Now here's the thing, when you're talking about computers, these are amazing and wonderful techniques because computers, in the snap of a finger, can do that for you. You can go to 0.01 or 0.001. In fact, your TI-83 can do this. And I don't want to show you yet. But again, this is just showing how we kind of build to the real calculus. So this Riemann sum for rectangles. The left side approach says the area is approximately f of a times delta x plus f of a plus delta x times delta x. You know what? Let me write this slower so I don't have to squish everything. Sorry about that. It's about f of a times delta x plus f of a plus delta x times delta x plus f of a plus 2 times delta x times delta x plus, and then you keep going until you get to f of b minus delta x times delta x. What am I doing inside of the functions? I just keep adding the width. So f of a in this instant was 0, and the delta x was 1. So if you add 1, you get to the next function value, f of 1. And you're going to add it one less time, because if you added it one more time, you'd be going too far. So that's why you start at f of a being the height. So this is just a bunch of heights times width. That's a height times a 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 width. You're just adding up a bunch of heights times widths. There's some summation notation used for this. Again, I'm not really going to get into that. We're just going to leave it as is for now. What did I want to say? There was one more thing I wanted to say in this section, and I cannot, for the life of me, remember. Oh, I know what I want to do, the right side approach. So we did the left side approach. Now let's do the right side approach. The right side approach. Ooh, that was ugly. Let's try that again. That was a little wider before, wasn't it? That's good enough. Okay, so here's your 5. That height is 25. Let's go 1, 2, 3, 4. That's not good. 1, 2, 3, 4. That's better. And the heights, that's got a height of 0, then a height of 1. Then this has a height of 4. This has a height of 9. This has got a height of 16. And then way up there a height of 25. So now we're going to do right-handed rectangles. Same delta x, we're still going to do a width of 1. But now we're going to use the right side. So for this first one, instead of trying to anchor it at a height of 0 and making no rectangle, we're going to anchor it from the right side, which means we have a height of 1. So there's our first one. Then our second one, anchoring it from the right side, you have this as your rectangle. And the next one would look like this. And the next one would look like this. And then the next one would look like this. So this is definitely going to be an overestimator. All of these areas, this area, this area, this area, this area, this area, that's too much. Just like last time, all those little spaces were too little because they were below. See, that was too much. These spaces right here, this was missing section, missing section, missing section, missing section, completely missing. All right, so again, each of these little delta x's, the width is 1. So this shows that delta x is equal to 1. Same for all of them. And then you just use the heights based on the right side of them. The area, you approximately these 1, 2, 3, 4, 5 rectangles. So A1 is here, A2 is here, A3 is here, A4, and then A5. So the first one has a width of 1 and a height of 1, so that's 1 times 1, plus. The second one has a width of 1 and a height of 4, so 1 times 4, plus. Third one has a width of 1 and a height of 9, plus. The fourth one has a width of 1 and a height of 16, plus. The last one has a width of 1 and a height of 25, which is 1 plus 4 plus 9 plus 16 plus 25. 5 and 9 is 14, plus 16 is 30, plus 25 is 55. So that was an overestimate. And I mentioned earlier that the exact area is actually 41 2/3. And if you average 55 and 30, you get 42.5. Which is only 0.9 away from the actual answer. That's why I said one of my favorite things to do, it's just a simple concept in terms of numerical mathematics. I love just averaging the left and right hand anchored versions of these. When you're doing computational math, again, this is something we're not going to be doing in here, but it's still important to appreciate the actual analytical calculus. Because like I said, the first picture, that very first one when it was just a boring old rectangle or a series of rectangles, you know the geometry formula for that one. When it's a triangle, you know the geometry formula for that one. And we know a couple other ones, but we don't know infinitely many geometry formulas. We don't know a geometry formula that would tell you the area under a parabola or any of these other really kooky, crazy curves. So that is why this is so important. So in a real calculus class, we show you how this Riemann sum, how this thing right here, you use a sum notation, you show that it turns into an integral and everything is hunky-dory. Fortunately for us, we just kind of use observations and leaps of faiths, well, we observe that, hey, we got geometric answers to match answers using a calculus formula, so it must mean that integration gives us area under a curve. And it does. All right, so once again, in the spirit of the fact that we have a test coming up, I don't want to get too far ahead. I don't want to end up 3 and 4 sections past where we're testing on. So I want to go ahead and call it here. Having finished 4.2, which is a section that I am not going to officially test you on because the problems are these types of things, but generally in the homework, these delta x's aren't a 1, they're much smaller, which makes the problems much more of a headache. Again, if this was a true calculus class, we'd be doing these for a week or two. In summer, a week. I don't want to say 2 weeks. So next class.
So ignore that last little part. All right. So we're gonna go ahead and take our break. What we got? 8:12. Let's come back at 8:20. And we will pick up with the next section. All right, so whew, this cold is killing me. Hold on. Aren't you glad you don't have to listen to this for an hour or 2 hours in one night? So we're gonna pick up where we left off. We just finished 1.2. We're gonna do 4.3, where instead of thinking about all those little rectangles and everything, we're gonna have it be a little easier to define some formulas, kind of like we did with derivatives, where we started out doing the limiting process and then got to some easier formulas. That's how we like to do antiderivatives, aka integrals, as well. So I don't waste any time. Here we go.
Bad habit. Areas and definite integrals. Let me go ahead and give myself lots and lots and lots of space so I don't end up with that formatting issue later that you've seen me have dozens of times, maybe not dozens of times, but several times. So as a reminder, indefinite integral is for a given function f of x is capital F of x equals the integral symbol, then the original function, and then you throw that dx in. So again, the integral symbol and the dx go in every single one of these types of problems. And we said that we don't have to give you an original function. We could give you a derivative, and then you just say the little f is the integral of the f prime dx. Or for a given function f prime of x, then it would be a little f of x is equal to integration symbol, and then the f prime of x dx. And we saw in the last section that this integration formula is very, very, very related to the area under a curve. The indefinite integration was related to the area under a curve. But we didn't exactly, I don't want to say this, we didn't give out every single layer of detail to it. We just did kind of this observation where, okay, we went from 0 to 5 on something, or 0 to 4 on something, whatever it might have been. And we saw that if you plugged in the largest value into the integrated function, that we got what happened to be the area under the curve when we did the rectangle and the triangle. But that was because we started at 0. We don't have to start at 0. We can start at 1 or 2 or 9 or 15 or -3. So we have to generalize a little bit more. We can't just say to plug in the largest function value into the capital F or the integrated function, and that gives you the area under the curve. There's a little more subtle detail to it. So more specifically, the integrated formula, the integrated function, excuse me, gives you the area under the curve from x equals 0 to x equals, let's just say b. If you insert b into the integrated function. What I'm saying here is, we got a graph. And our curve looks something like this. So this is the regular function, not the integrated function. And let's say we have just a B right here. Draw a little dotted line there, and then here's a point that was a little high. Here's the height f of b, little f of b. So the area from 0 to b is equal to capital F of b. That's not little f. That's not the same thing. This is little f of b. This height right here was the actual function value. This would be integrating the function and then plugging it in to b. Now, you don't plug the b into the function and then integrate. You have to integrate the function and then plug it in. So the area under a curve is represented by plugging in. Again, only if you're starting at 0. Is just plug in the right-hand x value into the integrated function. But what if you want to start it somewhere besides 0? Think about separate areas. So let's say our goal is to find the area from A to B. So same, just random function curve. This is our f of x. But now we want to go between A and B. So this would be the area between A and B on the x-axis. So check this out. Let's do 2 different integrals. Think about what capital F of A is, capital F of B is, and what simple operation could lead you from these 2 areas to 1 area. Again, we don't want to go from 0 to B. We have that picture up here. We want to go from A to B, but just plugging in B does the area from 0 to B. If you plug in A, it does this area from 0 to A. So let's dissect this. Let's show what this writing on the right side I just did. Let's show what both of those would be. So I'll do that in blue. Black for this. Black for the function part. So there's our f of x. Here's A. Here's B. And I'm going to show another one. Don't worry about if these functions don't look exactly the same. And then A seems to be about the peak. B seems to be about the valley. So on the left one, this left image, I want to show you what the area is going up to A. This area right here would be represented by f of A, because we're going from 0 to A. if I do f of b, it covers all of this area. Not just up to a, not between a and b, all the way from the y-axis up to b. So I showed you where a and b were in each of these graphs, but b was irrelevant for the first one, a was irrelevant for the second one. Now there's really not a lot to do from here, believe it or not. Think about what f of a is, which is whatever this number area would be. Think about what f of b is, which would be this area. And what simple operation could lead you from these two different areas? The x looks a little funny. To one area between them. One simple mathematical operation. What could you do with f of a and f of b? What could you do with these two values to get this one? Well, let's pretend that f of a, this area was 10. Let's just pretend for a hot second. So in this green, we're going to pretend. If we pretend that this area was 10, and if we pretend that this area is 40, again, all of it, all of it, all of it. So this little area here is 10, and then this entire area all the way up to b is 40. So again, I'm talking about this whole area, that's the 40. And then this little area, ooh, that was a terrible, terrible line. And then this area is the 10. So this is where I'd love for someone in class to say, but I know it's a different situation. If this is 10 and this is 40, then if you wanted to know what this extra area here is, the area from A to B should be 30. Because this was 10, and then whatever is here is just being added to the 10 to give you a total of 40. Well, we're thinking backwards though, so instead of adding, guess what we do? We subtract it. If you took 40 and 10 and subtracted them, you'd get, guess what? 30. So this is just the difference of the two areas. Which gives us what is known as the fundamental theorem of calculus. The fundamental theorem of calculus. It's kind of interesting in math classes. You tend to get a fundamental theorem of something. When you're in pre-calculus, you get the fundamental theorem of algebra, which states that for a polynomial, you can only have as many equations as the largest degree, as many solutions to the equation as its largest degree. The fundamental theorem of algebra isn't learned until you've done like 2.5 years worth of algebra. That's kind of weird, right? If it's fundamental, why wasn't it the first thing you do? Well, the fundamental theorem of calculus, this is, I mean, week 7, right? And now we're just getting to the fundamental theorem of calculus. It's not saying it's the first thing we need to do. It's just so important that it's fundamental to an entire subject matter. So yeah, we were able to do a lot of stuff before. We were able to do derivatives, we were able to do limits, but in terms of the other side of calculus, this area side, this is the fundamental theorem of it. So the fundamental theorem of calculus says that the area under a curve between two x values, a and b, is the following. And there's two different ways to write this. You have your integration symbol, but now you put numbers or letters for now on the bottom and top of it. So these a and b are generally numbers going between, say, 1 and 10 or 2 and 5, or 0 and something, or -6 and +6. And then you have your little f dx. So when we write our integration with numbers below and above it, like this, that says we're actually finding an area under a curve. Without these numbers, we're not necessarily finding the area under a curve. We're just integrating for other reasons. When you do it, this is equal to the integration at the right value, which would be the area up to that value, starting at 0, but then you subtract the area up to the first value. See, that's what we do. This right here, if this is 40, this area has to be 10, this area has to be 30 to make the whole thing 40. So if you have the whole thing as 40 and you know the first thing is 10, you subtract it off to get the 30, the area that you actually want. So this is known as the definite integral. Indefinite means you're not finding an area. Definite means you are. And a lot of applications, we're usually doing the definite integral. So this is one way that things are written, but sometimes people want to have some extra notation in the middle. Oops, wrong color. So in case you ever see this, and you will with me, the capital F with a vertical line behind it and then A and B. This means the same thing as exactly what you see on the right-hand side. F of B minus F of A. All capital Fs, all integrated formulas. So you can say that the integral from A to B of a little f is equal to big F evaluated between A and B. When I said there were two versions of this formula, that's the two versions. Because this thing right here is the same as the subtraction. So this vertical line and then the A and the B, that's just signifying to plug in the upper and lower limits. That's what those are known as, the upper and lower limits or upper and lower bounds. So finding an area under a curve is not really any more complicated. You still have to do an integration. It just means you're going to be plugging in two values into it and subtracting what you get. So again, integrate, then plug in. Integrate and then plug in the upper and lower limits. Some people will say left and right hand limits. That works too. All right, so let's try this out. Yeah, I can fit an example here. On the area under the given curve as a function. For A, we've got the integral from 0 to 3 of x squared dx. I said I'd do an x squared first. I think I was going from 0 to 5 in the last class's lecture, but that's okay. When we were doing the approximation, that is. And in fact, I can do this from 0 to 5 really quickly after the fact. So this is the original function. This is the lowercase f, the x squared. To find the area under the curve, you have to integrate this. So the 0 and the 3 don't come into play yet. We're going to go ahead and integrate the x squared. So we're going to apply our power rule. We add 1 to the exponent, and then we divide by the same value. So x cubed over 3. Adding 1 to 2 is 3, divide by the same value. Now, I'm going to do this one and only one time. When you integrate, you usually have this plus c, right? So I'm going to put it here for now, but you're going to notice something cool at the end. So we're evaluating this between 0 and 3. This is the way I like to do things. Just make my c a little nicer. There we go. So x cubed over 3 plus c, and we're evaluating between 0 and 3. So that was this extra little notation I mentioned here. I was also supposed to do this in red, but oh well, no big deal. Okay, so plug in the upper limit first, then do a subtraction and plug in the lower limit. This is the function. This is all we can do. We can't even clean this up. So we're going to plug in the 3. So equals 3 cubed over 3. So this is what became the 3. The other 3's are just coincidentally there. Plus the c. Then we go minus. So this was the f of 3. This right here would be capital F of 3 in theory. Now we got to do the lower limit. So we do f of 0. We're just plugging 0 into this thing. So 0 cubed over 3 plus c. And this is where I would leave this in class and say, does anyone think anything's wrong here? And then hopefully someone says yes. So this right here was the capital F of 3. This right here is the capital F of 0. And we're supposed to be subtracting those things. It's supposed to be this thing minus that thing. But there's extra terms. That's not being subtracted appropriately unless we wrap it in parentheses. This happens 99% of the time, that you need a parentheses around the second one. So let's see what we get. 3 cubed is 27, so that's 27 over 3. I'll show the extra work. Plus c, distribute the minus. 0 cubed is 0, so 0 cubed over 3 is 0. I'll write that for now. And then minus c. Well, 0 divided by 3 is 0. That's gone away. 27 divided by 3 is 9. And c minus 0, c cancel. That c and this c cancel. So the answer is 9. The area under the curve from 0 to 3 is 9. Please note, the c's always, 100% of the time, cancel. If you're going to do your integration with the c there, when you actually plug in your upper and lower limits, that c will be positive for the first one, negative for the second one. They will always cancel, which gives us the very super important memo: never use c when doing definite integrals, as it is pointless and always cancels. You don't have to do it. And I alluded to this fact last time. I was like, you know, we see that area there, but there was still a c. What's up with the c? This is what really happens with the c. So those capital F's, when you evaluate them, like so, they cancel each other out. So again, the c is only necessary for indefinite integrals. So you have to be careful as a calculus student. If I give you a problem that's indefinite, you better have a c. If I give you one that's definite, you can skip it if you like. You can just always put them in there, but then you're going to always see this tedious cancellation. I suggest that you practice this dozens and dozens and dozens of times to get used to when you need a c and when you don't. All right, so before we get to B, let's just do an alternative version of A. Let's go the integral from 0 to 5 of x squared dx, because that's the one I believe that we related to back in 4.1, or 4.2, excuse me. Let me see. I just want to confirm that. X squared, yep, from 0 to 5. So we did an approximation and we found one of the approximations to be 30 when we did an under approach. Then we did an over approach and we found the approximation to be 55. And I even gave you what it really is as a spoiler. But now let's see what it really is. So a left-hand rectangle approach said the area was about 30 with a width of 1. So, I mean, that's okay, but it's really not that accurate. Using a right-hand approach with a width of 1, the area was about 55. And again, if you want more accurate areas, make these widths 0.1 or 0.01 or 0.001, whatever you want to do that's smaller. The smaller they are, the more rectangles you have, the more accurate of an area you get. But we're not doing any of that jazz. We're doing the exact fundamental theorem of calculus. So, well, we already know the integral is x cubed over 3. We now know we really don't need the plus c, so I'm not going to write it anymore, ever again, when I'm doing definite integrals. And we're just going between 0 and 5. So we plug 5 in the first time. That's 5 cubed over 3. So that's the f of b, if you will, capital F of b, minus, now plug in the 0. That's 0 cubed over 3. 5 cubed is 125 over 3, minus, well, that's 0. So 125 over 3 is the exact area, which if you convert that to a mixed number, that's what, 41 2/3. So that is the exact area under the curve from 0 to 5. It's about 42. The approximations we had, the under was 30, excuse me. So when we did the left-hand one, we had a 30 as in our approximation. When we did the right-hand one, we got 55 as our approximation. What's cool is, and this isn't always super accurate, this, depending on the polynomial, this doesn't have to be super close, but if you average 30 and 55, I said this is kind of a classic way of getting a better approach. If I then divide that by 2, we get 42.5, which the real area was 41 2/3. This is only off by 1 now. So by averaging the lower version and the higher version, we actually get a much more accurate one. Now again, this doesn't have to be it doesn't have to be significantly accurate. It could still be a ways off, but it is usually the best of the 3. Usually, it depends on the polynomial. If you've got some super crazy, wacky polynomial that's all over the place, it wouldn't bend back. That was an error. But if it's all over the place, it doesn't have to be great. But again, for us, we're not a true calculus class. We're not doing numerical methods. So don't worry about that idea. But it is still cool to see, and I think you can appreciate that. Okay. So again, this is our primary focus in here. Doing integration formulas like power rules, logarithm rules, exponential rules, and then some fancier techniques we'll have in coming sections. So getting a function and then just jamming 2 numbers into the function to get the answer. That's it. It's just arithmetic from here. Now, you're going to have fraction arithmetic to handle. Remember, you're supposed to be able to do this stuff without calculators. So make sure you know how to add and subtract your fractions. That is going to be a very common issue. All right, B. Let's go with the area under the curve from 0 to 5 of x dx. I'm curious, how far did I go on the last one? Oh, my calculator symbol looks different. This laptop must have updated. That's funny. Either that or I'm crazy and misremembering, but I'm pretty sure that looks different. And I know this computer reset and installed Microsoft Edge or whatever they're calling the abyss that was Internet Explorer now. So I'm just curious how far we went on this one. Here was our line. We went to 4. We're just going to go to 5 this time. And we knew this one was exact. We found that and we showed that it was exact. So hopefully you have enough faith at this point to trust me. So now we're going to do the area from 0 to 5 under the curve of x. Now I'm starting these at 0. You don't have to. This formula allows us to start at any value and end at any value. I'll start doing different values next. Don't worry. So we go ahead and integrate. We take this x, which is really x to the first. That's not a prime. That's an exponent of 1. So we're going to add 1 to that and get 2, and then divide by the same value. This would be x squared over 2. That is the antiderivative of x. Now, we don't put the dx anymore, and because of the limits, we know we're finding an area. There's no c. We just go, hey, we're evaluating this from 0 to 5. That tells us the window of the area we're finding. So we plug in the 5. That would be 5 squared over 2 minus, plug in the 0. 0 squared over 2. And these don't have multiple terms, which is why I didn't need a parentheses around this. It's not wrong to do that, but you don't need it. 0 squared is 0. 5 squared is 25. So that's 25 halves minus 0, which is just 25 halves. Or as a mixed number if you prefer, 12 and 1/2, or as a decimal, 12.5. Unless my math lab is specific, it should accept all three formats. If you ever give an answer on a test that is correct, but just in a format they didn't want, you can let me know, and I'll give you full credit. I do not care one iota if your answer is a mixed number or a improper fraction or a decimal. If it's right, it's right. If this was a pre-algebra class and the whole point is to understand the differences of those three versions, that's another story. But we're clearly not in pre-algebra. All right. So B in particular, this is one you could actually check geometrically. You could find the area, excuse me, under this curve using geometry. And I'm not going to show that work. I will point out what it looks exactly like, though. It looks exactly like this, except you go to 5. So you'd end up, here's your graph of x, you go right one, up one. If you don't know how to graph x, that terrifies me. So there's the line of y equals x, but you're just going up to a height of 5 instead of 4. So you have a width of 5 and a height of 5. 5 times 5 is 25, but you half that and you get 25 over 2. That's the area of a triangle, 1/2 base times height. So 1/2 times 5 times 5. So I said it, but I didn't show it. All right, let's get a little different. Let's go from 3 to 8, and let's have our function be 7. So our function is constant. We still have to have the dx at the end. Hold on, I got a cough. So this right here is a constant function. This is more similar, just going back to previous problems, to this one. Sorry about that. But this was the function with a height of 15, and we even had this be a real life kind of example. So this function had a height of 15 and ended up drawing a rectangle. We could do that geometrically. We're skipping all that though. We're doing the calculus. So this is a horizontal line with a height of 7. I'm not giving you a reason why it's 7, it's just 7. And we want the area under the curve from 3 to 8. So we just integrate. We integrate the 7. The integral of a constant is the constant times x, because the derivative of 7x is 7. So this was one of the 4 or 5 formulas we gave you back in 4.1. We had the power rule. We had the constant rule, which is actually an exception of the power rule. I technically don't even have to give you this. I could just give you the power rule. We had the natural log rule and the natural exponential rule. And then an alternate version of the natural exponential is an alternate version of the exponential rule as well, where there was a coefficient in the top. So that's why I said arguably 5 formulas. Now we would normally do a plus c here if this was indefinite, but it's not. So we don't, because it would just go away. We're evaluating this between 3 and 8. So we just take the x's and make them 8 and 3 with a subtraction between them. So 7 times 8 minus 7 times 3. This is the upper limit minus, this is the lower limit. 7 times 8 is 56. 7 times 3 is 21. And 56 minus 21 would be 35. If you don't trust that, here is the horizontal line with a height of 7 that represents 7 as a graph. Here's 3 on the x-axis. Here's 8 on the x-axis. This is the area we were finding, which is a rectangle. So it should be the vertical length, which we start at 0 and go to 7, times the horizontal length, we start at 3 and go to 8, which is 5. And guess what? 5 times 7 is 35. Again, these super ridiculously simple examples like 7 and x for b and c, you can use geometry to get the areas of them. Because this ends up forming a rectangle. This ends up forming a triangle for b. This ends up forming a rectangle for c. But for problems like a, x squared, when you drew that picture down here, when you draw polynomials that bend, there's no formula that gives us the area of this bendy part to these straight parts, which is why calculus is needed, especially as the functions get more and more complicated. All right, so let's keep going. D. The integral between -4 and +5 for the function x cubed. And the dx is just part of the integration symbols. So x cubed, we can power rule this. Add 1 to the exponent, divide by the same number. That gives us x to the 4th over 4. There's no coefficient to drag. There's no pluses or minuses. That's it. Do we need a plus c? No, we don't need a plus c because we're evaluating this between a left and a right endpoint. So we can't ignore it. You can still put the c in there as long as you don't only put it once when you get to the evaluations. It should be there for both of them so they cancel. So plug in the 5. You get 5 raised to the 4th power over 4. And that's it for plugging in the 5. Now plug in the -4. Now be careful, we're plugging in a negative. You probably need a parentheses around your x because of that. Without that parentheses, this will be wrong, 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 wrong. You might think the negatives, this negative cancel, they don't. Because that negative is raised to an even exponent, which means it's going to become positive. But you still have the subtraction out front. 5 to the 4th, it goes 5, 25, 125, 625. Those are our multiples, our exponentials of 5. Again, 5 times 5 is 25, 25 times 5 is 125, 125 times 5 is 625. Then over 4. Minus, so this minus here is this minus here. Now -4, a negative raised to an even is going to be a positive. There's not going to be a negative inside of the fraction. We go 4. 4 times 4 is 16. 16 times 4. Sorry, I got thrown off. I was looking at something else. 16 times 4 is 64. 64 times 4 is 256. So that's a positive 256 over the original 4 in the denominator. Now you might say, oh, 4 goes into 256 perfectly, so let's reduce that. And that's a terrible idea, because if you make this a whole number, guess what? 625 divided by 4 does not reduce as a fraction. So then you're going to have a fraction minus a whole number, and you're going to have to get an LCD, and you've just gone in a full circle. So don't reduce. If all of the fractions can't reduce to a whole number, don't reduce any of them until the very, very, very end. So pause on reducing this for now. Wait until you just have one fraction, because that will avoid you having to get an extra LCD. So if you do this subtraction, 625 minus 256, that's going to be a 9 at the end. 11 minus 5 is 6, and then 5 minus 2 is 3, so 369 over the 4. This does not reduce, so that's our answer. If you want that as a decimal or a mixed number, let's see, 4 and a 3, 6, that's going to be 90, another 2 from the 9, 92 and a quarter or 92.25. Or 92 and 1/4. I'm not going to write all three. Now, if that's a fraction that's like at thirds, you don't want to write that as a decimal because most people won't write the bar and then it's wrong. And some mathematical programs don't allow you to put a bar up there. I know my math lab at one point didn't used to, but I think now it does. So again, just something you have to be very, very careful with are your fractions. And you end up seeing a lot of fractions with this stuff. Now, how do I want to do this? Yeah, let's do it here. So I'm going to draw the graph of x cubed and represent the area from -4 to 5. Then I'm going to do 2 more examples. And I want to see if maybe first you can guess the answer off the bat. And second of all, if you can't do that, can you at least reason it out geometrically that it makes sense? So let's make this picture. And I will need, you know what? How do I want to do this? How do I want to do this? Let's put it on the next page. Save room for 2 more of these, and I'll go ahead and write what they're going to be. E, I'm sorry for being all over the place. I'm used to having a big old board and a TV screen and other media instead of just one thing. So this is more compressed. E will be the integral of x cubed from 0 to 5. And then F is going to be the integral from -5 to +5 of x cubed dx. All right, so before I do E and F, let's go ahead and go lower and paint the picture for D. So we were going the graph of x cubed from -4 to 5. And I can probably fit them all on this page, especially if I zoom out just a little bit. Okay. And I'll label them, it was D, E, and F, so graphs. For D, the right side of x cubed looks like this, the left side of x cubed looks like this. So this is our graph of x cubed, and we went from -4 to +5. So if this is -4 right here, +5 would have to be further away than that. So let's just say this is our +5. So the area that we just found was that. And what's unique about this problem is these areas are separated. There's a region over here, then a region over here. It's not like just one normalized looking geometric shape. This is a lot funkier than just a rectangle or a triangle, or even just the basic of the x cubed part, because I mean x squared. This looks like an x squared practically, but then this part over here is separated and it's also below the x-axis. Note that this area is below the x-axis. This means something. An area being above the x-axis and an area being below the x-axis is going to mean something, and I think we're going to be able to deduce that after we do the next 2 examples, do their graphs, and make some analysis. But anyways, this area from including here and here, that was supposed to be about 92 roughly. It was about 92. So same function, meaning when we integrate x cubed, we still get x to the 4th over 4. But now our left and right endpoints are different. For E, we're going between 0 and 5. Well, the 5 is the same, so that's 5 to the 4th over 4 minus. Now plugging in 0, you get 0 to the 4th over 4. 5 to the 4th is still 625. Over 4 is still there. That's a minus 0. So we get 625 divided by 4. Now 625 is bigger than 369, which means this area is bigger than the other area we just found. Specifically, 625 divided by 4 is about 156 and a quarter. So there are the areas. And then I want to draw the picture. So notice something about the numbers. When we went from -4 to 5, it was about 92. When we went from 0 to 5, when we made this a smaller region, the area was bigger. It was 156. It was almost 60 more. excuse me, it was 64 more. Why did I write a 4 there? That's a 5. I think I was saying the over 4 at the same time. So let's see what the graph of E looks like. I mean, we basically already drew it, but we don't need the left side anymore. We're just going up to 5. So here's that same shape. Let me make it a little steeper than that, though. That was kind of crummy. Nope. Flat, 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 steep. There we go. So the area we're finding is now just this. So this area combined was about 92, but this only one of the parts of the area. So we're cutting a portion off, and yet somehow the area is now 156.25. How is that possible? This is a bigger shape, right? This is more area. This is more coloring that you would have. I'm sorry, this was more coloring than you would have to do for the second one. So why is it humanly possible or fathomable that this area has a larger number than this one, which had more segments? It has everything to do with this right here. This area was below the x-axis. So this area over here was 156.25, just the right side. Then this left region, whatever area that was, it actually counts as being negative. Whenever your curve goes under the x-axis, any area is now going to be negative associated with that. So this left portion is a negative area, this right portion is a positive area. So again, this is a negative area, so this is like subtracting away from it. This is adding area. And you might say, well, Mr. Beckner, you can't have negative areas in geometry, and that's because this isn't geometry, this is calculus. So the x-axis counts as a divider, and when we do applications, that's where things start to tie together, that negative areas have an impact on positive areas. So let's look at F. Now with D, this side was kind of smaller, the left side was kind of smaller than the right side. Let's go ahead and paint the picture to F. Oops, wrong color. And let's see if you might be able to guess what the answer is. So we're going back to drawing both sides of this. Sorry for that little squirreliness there. And we're going from -5 to +5. So why did I write a negative there? Good Lord. Because I said negative at the same time. I'm getting much worse about writing and thinking and speaking at different speeds. So now we're finding this area. Now from 0 to 5, we already know that this little area right here, this area from 0 to 5, we know that's 156.25. We know that from here to here is 156.25 by above. Now guess what? If you go from 0 to -5, or -5 to 0, that's still the same exact shape. This height down here is the opposite of this height up here at 5. So I'm going to guess that this area right here is -156.25. That's my guess. Which means that the total area, these are opposites and will cancel, and thus would be 0. Because the size of this shape is exactly the same as the size of this shape. One of them counts as being a positive area, one of them counts as being a negative area, so when you add them together, they cancel each other out. This is kind of like having a loss one year and a profit the next year, where they match, so now you're just at $0. Let's see if the calculus mixed with the algebra agrees with this. So we know the integration is still x to the 4th over 4. We know that. Now we're evaluating between -5 and +5. So we go 5 to the 4th over 4 minus, little parentheses for this plug-in, -5 to the 4th over 4. 5 to the 4th is 625, so that's 625 over 4 minus. Negative 5 to the fourth is also 625. That subtraction is still in front though. Those are opposites, so they cancel. So even though, if you just thought of this in terms of geometry, this area would actually be twice of 156 1/4, which puts that at what, 312.5. But in terms of calculus, when we have positive and negative values of functions, which means when we integrate over time or over product numbers or whatever, those can still be associated with negatives in terms of an application. That's how areas can be negative. That's how areas can be 0. Yeah, in flat out geometry, there is no negative area. But in calculus, when we're dealing with applications, when we're integrating rates, you can get negatives, you can get zeros. Now you have to be careful here. Some people will always just go to the picture when they see a symmetry problem like this. Oh, from negative 5 to 5, it's always going to be 0. Let's do another one. Let's do the integral of x squared dx from negative 5 to 5. We know from 0 to 5, we already did that earlier. It was what, 125 over 3. If you draw this picture, where do I want to put it? Can I squeeze it? I'll squeeze it in over here. So if I draw this picture, x squared is all positive. X cubed, the left side goes down. X squared, the left side goes up. So here's our x squared graph. And we're going from 5 to negative 5. So if your teacher was a perfect artist, which that's terrible, much better. Here, I'll put the negative 5 here. Okay. So this is the area we're trying to find now. So you don't just say the area under the curve, because that would go infinitely into the negatives. We're going between the area under the curve and the x-axis. That acts as our other side. Do you think that the area here would be 0? Some people would say yes, because this area matches this area, so they cancel out. That's not the case. Areas are only counted negative if they're below the x-axis. This is not below the x-axis. This is not a negative area here. That's a positive area. But based on symmetry, from 0 to 5, this curve is identical. From 0 to negative 5, that height's identical. That curve's identical. So whatever this area is should be the same as this area. And we already know from 0 to 5, again, earlier we said it was 125 over 3. So this area, just the right side, was the 125 over 3. This is literally the same shape, just mirrored. So its area should be identical, not negative, because it's above the x-axis. If it was below, it would have been negative. See, this was negative because it's below. This is positive because it's above. So this area is 125 over 3. This area is 125 over 3. They're the same, so you can just double it. So the total area should just be 2 times the 125 over 3, which is 250 over 3. Let's see if that agrees with the actual calculus. So integrating, you get x cubed over 3, and you're evaluating between negative 5 and positive 5. So that's positive 5 cubed over 3 minus, use a parentheses for plugging in the negative 5 cubed over 3. 5 cubed is 125, so that's 125 over 3. Now this minus cubed stays minus. We still have the minus for the subtraction, so it's minus negative 125 over 3, which is a positive. Adding the same number twice is the same as doubling it. You get the same answer. What I'm trying to show you here is that you can use the concept of symmetry from pre-calculus at times to change your integration bounds and come up with an area. So if you know you have an even symmetry function, if the left side matches the right side with the x-axis, the y-axis is a mirror. So going from -5 to 5, you can just say, all right, well, I already know how to do from 0 to 5. Let me just double that answer, since the left area is matching the right area. Or if you're dealing with something that's cubic, which would be an odd function where the left side is the opposite of the right side in terms of height, then you could find, as long as they're symmetric, you can just say they're going to cancel each other out. But if they're not symmetric, if they're going from -4 to 5, just because you have a symmetric type of function doesn't mean you get some type of symmetric based answer. It's only when these are opposites of each other, like in example F, when it can zero out, or in example G, where it can double out. So these are very small cases that you can use when they happen, but how often does it happen? I don't know, 5% of the time, 2% of the time, 10% of the time, a small portion of the time. But if you get one of those situations and you recognize it, why not use it if it's convenient to you? Why would I want to use the idea of doubling the area instead of this? Well, maybe I'm a student who messes up plugging in negatives all the time, or fixing a double negative situation. That could be a mistake that you make by doing it directly, versus if you use some geometric reasoning and symmetry, maybe you can avoid those simple mistakes. But again, can't always do it. 0 to 5, you can't do that because it doesn't have two sides. -4 to 5, there's two sides, but they're not symmetric. 3 to 8, there's no symmetry there. So you do have to be careful when you're going to be using it. All right, let's step it up a little.
We'll step it up next time with a different example. We'll be going into example 2 for that section. But for now, just going to pull up that whiteboard again. So remember, your biggest issue on the table right now is test 2 on those limited sections of chapter 2 and 3. 18 questions, 2 hours, no notes, no books, no calculators. This will be the last no calculator test. 3.8's due tonight, 4.1 due in a couple of days, 4.2 due in a week. We'll finish 4.3 next time, so then that'll be assigned a week from then. And then eventually we'll start talking about test 3 as we get through more sections of chapter 4 and so on. But for now, we will be signing off. Hope everyone has a good evening. I hope everyone does as well as they can on the test. Don't forget that there are review materials available to you in my math lab. Those will be very, very helpful. And hopefully next time I'll sound a little better than this. All right, so take care, everyone. And also hopefully no more technology issues. So take care, everyone, and email me as always if you have any questions. Have a good one.